Our next speaker is Eva Philippe from Sorbonne. She's going to present her work on realizations of the s-permutahedron via flow polytopes. Please, the stage is yours.
So this is joint work with Daniel Tamayo Jimenez, who is now a data scientist in Paris, Rafael González de Leon from Chicago, Alejandro Morales from Montreal, and Marta Yip from Lexington. And to explain a bit the story behind this s-permutahedron, I start with the usual weak order on permutations. So this is a posed structure on the set of permutations of a given size n that has many nice properties. So it is a lattice in particular. And also its Hasse diagram can be realized as the edge graph of a polytope, the permutahedron. There is also a cousin story that is also very interesting. The Tamari lattice, which is a posed structure on any Catalan family, which has also many nice properties that it is a lattice, and its Hasse diagram can be realized as the graph of a polytope, the associahedron. And these two objects are related both at the combinatorial sides, because, for example, the Tamari lattice is a quotient of the weak order, and also the geometrical side. A generalization of the Tamari lattice was proposed by Préville, Rattel, and Vienneau. So they called it the new Tamari lattice, where nu is a parameter that is a certain lattice path. And they have a diagram that can look like this. And Ceballos, Padrol, and Sarmiento showed that the Hasse diagram of this new Tamari lattice could again be realized by polytopal objects, but this time a polytopal complex, which is more precisely a polytopal subdivision of the associahedron. So this is the new associahedron. And another realization was given by von Bell, González de Leon, Mayorga, Cetina, and Yip. This time, the Hasse diagram of the new Tamari lattice is the dual graph of a certain triangulation of a flow polytope of this graph, which they called the new caracol graph, where caracol means snail in Spanish. And the parameter nu gives the number of these green source edges. And the question raised by Ceballos and Pons 5 years ago is there a similar generalization as the new Tamari lattice, but for the weak order and permutahedron? And so they defined a combinatorial structure that they called the S-weak order, where S is now a vector of non-negative integers. So they have their combinatorial objects that are S-decreasing trees, and they put a posed structure on it that has nice properties. For example, it is a lattice, and we can recover from the S-weak order, we can recover some new Tamari lattice by taking quotient lattices. And they conjecture that, again, the S-weak order, the Hasse diagram could be realized as the edge graph of a polytopal complex that would be even a polytopal subdivision of a permutahedron. And they also gave the combinatorial definition of what would be the higher dimensional faces of this object, the s-permutahedron. So this is the conjecture that we solved, with the only restriction that our techniques only work for S being a vector of positive integers, so there are no zeros. And our techniques, we first use also flow polytope, this time of a graph that we called S-oruga, and then tropical dualization, and we could provide really precise coordinates for realizations of the s-permutahedron. So to explain briefly what this S-weak order is, so the objects are given by Ceballos and Pons are S-decreasing trees, so from a vector S of length n, for example, 1, 2, 2. We say that an S-decreasing tree is a planar rooted tree with internal nodes labeled from 1 to n that is decreasing, and such that the nodes labeled I has Si plus 1 children. So for example, here the node 1 has 2 children, and nodes 2 and 3 have 3 children. So here there is the set of all 1 to 2 decreasing trees, and Ceballos and Pons put a poset structure on these S-decreasing trees with a certain rotation operation that I will not detail because it is easier to see in this other setting valid when S has no zeros. So when S has no zeros, S-decreasing trees are in bijection with S permutations, also called Stirling S permutations. So the bijection is as follows. We read the labels of the nodes by going from left to right along the tree. So if we follow this orange arrow, we first read a 3 below the node, then a 1, 3, 2, and 2. So this is how we go from this S-decreasing tree to this S permutation 3, 1, 3, 2, 2. So all S-decreasing trees are in bijection with multi-permutations that have SI occurrences of the letter I and that avoid the pattern 1 to 1. This is for the decreasing condition. And now, and also we recover the usual weak order when S is equal to 1, 1, 1, 1, because then we only have all the permutations. And the cover relations of the S weak order are quite similar to the usual cover relations of the weak order with transpositions. But now, sometimes we need to transpose a block because we have this 1-to-1 avoiding condition. So, for example, with this orange arrow, we transpose this whole block 2, 1, 2 with the next 3 to have 3, 2, 1, 2, 3. So this is how we get this S weak order. And as you can see here, that we have the Hasse diagram looks like a subdivision of a hexagon. And this was a Ceballos and Pons conjecture that for any S, the s-permutahedron can be realized as a polytopal subdivision of a combinatorial permutahedron. So they could provide realizations for dimension 2 and 3, but they could not go to higher dimensions. Also, another quick example where S is 1-to-1 because it will be my running example. Now, these are our 3 realizations. So I will mainly focus on the first one. So we go from the combinatorial faces of the S-permutahedron with a bijection that reverses inclusion to the interior cells of a certain triangulation of a flow polytope, which has this big dimension. So this is a first realization, but it has a high dimension, and also it is dual, because our object, the S permutations, will index the maximal cells of a triangulation. Then the next step will allow us to reduce the dimension and go to a mixed subdivision of a sum of cubes of dimension at most n. So we lower the dimension, but we are still in a dual realization. And at the end, we have a dualization step that gives bounded cells of an arrangement of tropical hypersurfaces that gives really explicit realizations of our S-permutahedron, and we can show that it is indeed a subdivision of a permutahedron. And here are the tools that we use. And I will start with the flow polytope story. So the general context about flow polytopes is that we have a graph G on labeled vertices, for example, from V0 to Vn+1. And we consider the edges to be oriented always from the smaller to the greater vertex. When we have such a graph, we say that a flow is an assignment of weights on the edges that are non-negative, and such that there is a conservation law, which is for each inner vertex of the graph, the sum of what goes in has to be equal to what goes out. So for example, here, 0.2 plus 0 is equal to 0.1 plus 0.1. And also, the sum of what goes out of the source is equal to 1, as well as what goes into the last vertex, the sink. So we can think of these as the repartition of a unit 1 of water flowing through the graph. When we have such a flow, we can see this as a point in the space of edges of the graph. And when we collect all the possible flows on our graph, we obtain a polytope, which is called the flow polytope of the graph. And some geometric properties of this flow polytope can be understood with combinatorial properties of the graph. For example, the vertices of the flow polytope are in correspondence with routes of the graph, which are the path from the source to the sink. So in this example, with 6 edges, we in fact have a 3-dimensional polytope, which is this pyramid, and here we see the bijection between the vertices and routes of the graph. Another nice feature of the flow polytopes is that they have nice triangulations. And certain families of these of nice triangulations of flow polytopes were provided by Danilov, Karsanov, and Koshevoy by the means of framing. So this is an additional structure that we put on our graph, which is for each inner vertex, we choose an ordering of the ingoing edges and an ordering of the outgoing edges. So in this drawing, I represent these orderings with little numbers. And in this drawing, I changed the drawing of my graph so that I can read the framing by reading the half edges from top to bottom. And when we have this notion of a framing in our graph, there is a notion of routes that are crossing and routes that are not crossing or coherent. And what Danilov, Karsanov, and Koshevoy showed is that if we take the maximal clicks of pairwise coherent routes, we can see these clicks as a subset of vertices of our flow polytope and take the convex hull of this subset. And if we take all possible maximal clicks, we will obtain all the maximal cells of a certain triangulation of the flow polytope that we will call the DKK triangulation that has nice properties. For example, it is regular. We will come back to this later, and also unimodular. In our example, we would obtain this triangulation, for example. OK, and so knowing this DKK triangulation, we can play with our graph and do combinatorics and have a geometric construction out of it. And when we had the idea to use these techniques for our s-permutahedron problem, we needed to find a graph. And this is the graph that we came out with. So we called it the S-oruga, because oruga means caterpillar in Spanish. So it goes as follows. We have n bubbles that are made of 2 edges, top and bottom, between vertices vi-1 and vi. And we add an additional source vertex linked to v0 and si-1 source edges going to the vertex vi. So here we see that we really need the si's to be at least 1 for our construction to work. And we read the framing also from top to bottom, so always the top edge first, then all the source edges, then the bottom bubble edge. And with this framed graph, we know from the KK theorem that the maximal clicks of coherent routes will correspond to maximal cells of the DKK triangulation. And we showed that these maximal clicks are in correspondence with our S permutations. So here is an example of the correspondence, again with S is 1 to 1. And if we take the multi-permutation 3, 1 to 2, we take the following maximal click. So we will always start with the route with only top bubble edges. Then we will push downward the bubbles when we read the multi-permutation. So first here we read a 3, so we will push downward the third bubble edge. Then we read a 1. And then when we read a first 2, we go from this top bubble edge to the source edge that goes to V2. And then when we read the last 2, we go to this final only bottom edges route. So we have the bijection between the S permutations and the maximal cells of the DKK triangulation, and we could show that the other faces of the s-permutahedron are in bijection with all the interior cells of the DKK triangulation, which means the cells that are not on the boundary. So in particular, the Hasse diagram of the S-weak order, so the vertices and edges of this s-permutahedron, is the dual graph of this DKK triangulation. So this is first nice geometric realization, but it is dual, and it has dimension the sum of the SIs, which is greater than n. Okay, so, and this is a picture of, for S is 1 to 1, of the dual graph of this DKK triangulation, where the vertices are indexed by the S-decreasing trees, the S-permutations, and the maximal cliques of routes. So we did this first step, and now the second and third steps are first to reduce the dimension. I will present the Cayley trick, and finally this tropical dualization step. So in general, for the Cayley trick, we have a family of K polytopes living in the same space R to the D, and we have two constructions from this family. The first one is called the Cayley embedding, and it lives in a D plus K space because we embed each of the K polytopes at a different coordinate. For example, if we take this triangle and this quadrilateral, we would obtain such a three-dimensional polytope. And the second construction is the Minkowski sum, so it lives in the same space, and we take all the points that are sums of points in our polytopes. With this same example, we would obtain this green polygon. And in fact, when we take the Cayley embedding and we intersect it with a well-chosen subspace, so here it would be the plane that hits in the middle of the segment between these two polygons, we recover the Minkowski sum. And when we have a subdivision of the Cayley embedding, we will have what is called a mixed subdivision of the Minkowski sum, which means that the cells of the subdivision respect this Minkowski sum structure. And also, when we have regular subdivisions of the Cayley embedding, this will give regular mixed subdivisions of the Minkowski sum. And we could use this trick in our case because, in fact, any flow polytope can be seen as a Cayley embedding of smaller flow polytopes. And in our case, there are two nice ways to do this, to see the flow polytope as Cayley embeddings. Each time with flow polytopes of only bubble graphs. So these flow polytopes, in fact, give cubes. So in one case, we always have an n-dimensional cube and strictly smaller dimensional cubes. So when S is 1 to 1, we would have this three-dimensional cube and a segment. And so the mixed subdivision corresponding to our DKK triangulation would be this one. And in blue, I highlighted the cell corresponding to this maximal clique or to this S permutation. Or another way to do the Cayley embedding, or we can see this as cutting this cube. We will have two n-1 dimensional cubes and smaller dimensional cubes. So here we would have two squares and a segment, and this would be our mixed subdivision, again with this blue cell. So now we again have a nice geometrical realization with a mixed subdivision of a sum of cubes. And the last step is to dualize these constructions, and the convenient setting to do this is to use tropical geometry. So the general setting is that when we have a point configuration living in a space R to the D, and the lifting function which associates to each of our points a certain height, a real number, we have already seen such drawings, we can lift our points to one dimension higher and look at the lower faces of the convex hull of these lifted points. And this will give us, so these faces will give us cells of subdivision of our point configuration that is said to be regular because it comes from this lifting process. Another thing that we can do with these points and lifting function is to encode them into a tropical polynomial where the exponents of the monomials are given by the coordinates of our vertices and the coefficients by the lifting function. And when we have seen that when we have such a tropical polynomial, it is associated to a tropical hypersurface, which is the locus of the points where the minimum of this function is attained at least twice. And the theorem, a folklore theorem, is that the cells of the regular subdivision are in correspondence with the cells of the tropical hypersurface, where we also take into account the maximal dimensional cells induced by the hypersurface. So, for example, with the 4 vertices of this square and the lifting function 0, 0, 0, 1, we would have this tropical polynomial and this pink tropical hypersurface. And we can see that the vertices are in bijection with the 2-dimensional cells and the 1-dimensional edges with the 1-dimensional cells, and so on. And we, moreover, showed that the interior cells are in bijection with the bounded cells of the tropical hypersurface. So, for example, here we have these 2 triangles and these diagonal that are given as the faces of the regular subdivision induced by the lifting, and they are in correspondence with the 2 vertices and this small edge. Moreover, this tropical dualization process behaves well with the Cayley trick. So when we have a Minkowski sum of point configurations, each with its own lifting function, we will have an arrangement of tropical hypersurfaces. So this is what we do in our case. We have seen that we had a Minkowski sum of cubes. And in fact, we also have lifting functions that are given by Danilov, Karsanov, and Kochevoy, because in their theorem, they say that they have a regular triangulation, and they provide an explicit way to build the lifting functions, so we could use them and associate to each of these Minkowski summands a certain tropical hypersurface. So in this example, we have these 3 tropical hypersurfaces. And if we restrict to the bounded cells, we have exactly the faces of an s-permutahedron. So we could really give very explicit coordinates for this s-permutahedron whose vertices correspond to our s permutations. Sorry. So this is a bit a recap of the 3 steps of the construction. And some perspectives to finish. So a second question asked by Ceballos and Pons was that, so they conjectured that also we could have realizations of the s-permutahedron such that we can obtain realizations of the s-associahedron from it by removing facets. And in our case, with our construction, we have a way to go from the S-oruga to the S-caracal graphs, but we don't understand very well how the geometry behaves, what is the geometrical behaviors. And also a second natural question is to deal with the case where there are zeros in the parameter S. And we could not find a relevant graph in this case, sorry. But with very different techniques, with Vincent Pilot, we were able to build to answer these 2 questions and build geometric realizations of all lattice quotients of the S recorder, and even in the case where there are some zeros, but very different techniques, no flow polytopes. Another question would be to still consider this S-oruga graph, but other framing lattices. Do we have other interesting combinatorial families? And this is related to the next talk by Matthias von Bell. And finally, we could wonder about other Coxeter types. So these are realizations that we obtained in dimension 3, and thank you for your attention.
Much for the talk and for the pictures. Are there any questions?
So my question is, was it difficult to try to find the framing and also the graph for the s-permutahedron, or do you have like some notion to say, no, it's like the oruga, but with extra things, or is what?
So we tried a lot, but also the intuition behind the graph is that some nice things that we have with the flow polytopes is that there are formulas for the volume, and so we knew that it is quite easy to compute the volume with this formula of this graph, and we knew it would give the number of S-decreasing trees. So we were expecting to have, because the DKK triangulation is unimodular, if we have the right volume, then if we will have the right number of simplices. And then to find really the framing, and yes, we tried before arriving to this graph. Okay.
Any further questions?
I just wanted to ask, so for the permutahedron and the isosahedron, the underlying orders, they are lattices. This is also true for these S cases, right?
Yes, the S recorder is also a lattice, yes.
And for the isosahedron as well, right?
The s-associahedron also, yes.
Okay, thanks.
Yes.
Hi, thank you for the very nice talk. So when you decompose these Aruga graphs, or the flow polytopes for the Aruga graphs into Cayley sums, is that specific for this type of graph, or could you do this for more general graphs?
So not really. We can always express the. We can always express a flow polytope of a graph as the Cayley embedding of other flow polytopes. So the idea is here we cut along the source edges, and these source edges give the coordinates where we embed the smaller flow polytopes. But we could also cut at other places. So yeah, there are different ways to do it.
Hello, thanks for the very nice talk. I wanted to ask you something that's related to your last comment about the sardoplexes. Is that what you call it? How much of the story that is, like without the S remains, like the usual isosahedral, its normal fan is a coarsening of the braid arrangement, like these sort of things, do they still make sense?
Kind of, but we don't have a fan anymore because we have a polytopal complex. So we called it a foam with Vincent. And also, we also take Minkowski sums of, so the usual cases of shard polytopes, but now we don't have shard polytopes, but shardoplexes, which are polytopal complexes made of shard polytopes, each of them. So, but we can talk of this other story later, maybe.
Thank you.
So I would like to suggest that we move further questions to the coffee room. Let's thank the speaker again.